Warm greetings and welcome, dear audience. This is Dr. Estamala, your firstly and successful global educator, SDG, ESG, STEM, and technology enthusiast from Malaysia. Join our exclusive research series on masterclass on STEAM and featuring latest technology and management skills designed for university students, college learners, and working professionals. Led by distinguished academicians and industry experts, this program explores cutting edge innovation in management, science, technology, engineering, arts, and mathematics. Gain insights into AI, robotics, data science, IoT, and more while understanding their real world application. This masterclass aims to enhance the knowledge, foster innovation, and create awareness of the rapidly evolving technological landscape. Yeah, for this professional masterclass, here we have dear respected um, Ambassador Professor Dr. Rania Lampu from Greece. Her topic, as usual, that is it will be a research on research series, advanced level. Yeah, today is the advanced level. First part one on tools and techniques publishing. Yeah, for this I would welcome our honorable and beautiful masterclass trainer today, Dr. Rania. Welcome.
Okay. Greetings from Athens, from Greek Ministry of Education. Thank you very much, Dr. Estera. Welcome all to this new session to advanced data analysis in academic research. And our aim today is to explore, as you mentioned, the cutting-edge methods, tools, and applications that are shaping the future of scholarly investigation, from predictive modeling and statistical inference to machine learning and visualization techniques. Advanced data analytics empowers researchers to uncover hidden patterns, to validate hypotheses with precision, and transform raw information into impactful contributions to science and society. So once again, welcome. And I would like, of course, to thank Elegant Empire Education and you, Dr. Estera, for inviting me and initiating this new series of research. So we'll start sharing my presentation now. Can you see now my presentation, Dr. Estera? Can you see now?
Yes.
Okay. Can you see also the change of slides?
Yes.
Okay.
Yes. Good to go. Yes.
So during our previous sessions, we discussed about data analytics. We have dedicated much time on this, but now I think since we can leverage amazing tools, machine learning and AI tools, I think it's time that we can move forward to a more advanced level in data analysis, more complicated. And it is important to clarify also some new concepts, more advanced concepts, and some new strategies and techniques. So first, we need to start from multivariate and complex statistical techniques. I guess we all know about ANOVA, and ANOVA actually this stands for analysis of variance. It's a statistical technique which is used to compare the means of 3 or more groups to define if at least one group mean is significantly different from the others. Why use ANOVA instead of multiple t-tests? Because running multiple tests increases the risk of type 1 error, so what we call false positives. And ANOVA controls when it's important to use ANOVA. Let's start from this. We can use ANOVA when you have one independent variable, when you have one dependent variable continuous, when you want to know whether group membership affects the mean of the dependent variable. So ANOVA controls for this risk by testing all group means simultaneously with a single overall test. So here we can see analysis of variance and when to use it. And I'll just give an example of this scenario. You want to test whether 3 different diets lead to different weight loss outcomes. The independent variable will be the diet type, diet A, diet B, diet C. The dependent variable will be the weight loss in kilograms. So ANOVA will tell you if at least one diet leads to significantly different weight loss compared to the others. So how ANOVA works? ANOVA compares between the group variance, so how much group means differ from the overall mean, and within group variance, how much individual scores differ within each group. The types of ANOVA, one way, when we have 3 more groups, here we can see one with 3 more groups, two-way ANOVA. And repeated measures ANOVA, same subject which are measured multiple times, and MANOVA when we have multiple times. Actually, it's an extension of ANOVA. So ANOVA, we could see that this statistical method used to compare the means of 3 or more groups, and to ensure that the results are valid, certain assumptions must be met. What are these assumptions? That independence of observations, what does mean? That it means that each data point should come from a different unrelated subject or unit. So one observation should not influence another. Example, if you are measuring test scores from students in different classes, each student's score should be independent, no cheating, collaboration, or repeated measures. So why it is important? Because validating this can lead to misleading results, since ANOVA assumes the variability is only due to group differences and random error. Another assumption, normally distributed dependent variable. What does this mean? That the dependent variable, the outcome that you're measuring, should follow a normal distribution within each group. For example, if you're comparing the average blood pressure across different age groups, the blood pressure readings in each group should be roughly bell-shaped. So this is normal. So why it is important? Because ANOVA relies on the idea that the sampling distribution of the means is normal, especially for small sample sizes. And note something, that ANOVA is quite robust to this assumption if sample sizes are large and similar across groups. A homogeneity variance, equal variances, this means that the spread, the variance of the dependent variable should be similar across all groups. For example, if group A has scores ranging from 10 to 12, and group B has scores ranging from 10 to 15, then variances are unequal. Why it is important? Because ANOVA compares between group variability to within group variability. If group variances are different, this comparison becomes invalid. You can test this with Levin's test or Bartlett's test in statistical software. So here we have a summary table. Independence observation means no influence or pairing between observations. So why this is important? Because it prevents biased results. Normality, that data, each group follows a normal distribution, so this ensures the accurate estimation of means. And homogeneity of variances, this means that groups have similar variances. And why this is important? Because it validates the fit-F test used in ANOVA. So what, this is the example that I mentioned before about the diets. ANOVA will tell you if at least one diet of the 3 types will lead you to significantly weight loss compared to the others. How this works between group variance, how much group means differ from the overall mean, and within group variance, how much individual scores differ within each group. Now, when we should use multivariate techniques like MAINOVA or factor analysis. MAINOVA is used when we have multiple dependent variables that are related or correlated, when we want to test whether groups differ, when our dependent variables are categorical, when we want to reduce the type 1 error that could occur if running multiple ANOVAs separately, when we want to assume homogeneity of covariance matrices and multivariate normality. Let's give an example. You are studying the effect of teaching method, traditional versus digital, on student outcomes, exam score, assignment grade, and class participation. Since these outcomes are likely correlated, MAINOVA is more appropriate than separate ANOVAs. So we have multiple dependent variables. We want to test whether group differs and when our dependent variables are categorical. We need to know about these requirements. And the factor analysis, which has 2 types, exploratory and confirmatory, it's used when we want to identify underlying structures or factors in a set of observed variables. When our goal is data reduction, we want to summarize many variables into fewer interpretable factors. When we are developing or we validate scales of questionnaires, psychology and education and social sciences, when we think that some latent variables explain observed patterns, and when we have continuous variables that are at least moderately correlated. Let's give an example about factor analysis. You want to give a 20-item questionnaire on workplace motivation. Factor analysis here can help define whether these items group into underlying constructs like intrinsic motivation, and job satisfaction. So when we want to define underlying structures or factors, when we want to move with data reduction, when we want to develop or validate scales or questionnaires, and when we have continuous variables that are at least moderately correlated. So MAINOVA, what is the key use case? Compare groups, group means, and the primary goal is to test the group effects on multiple outcomes. Factor analysis, the use case here is to reduce data, uncover latent constructs, and the primary goal is to identify patterns or dimensions. Because the type of variables also differ, MAINOVA will have categorical continuous. With factor analysis, we have continuous variables. So, what is the difference between exploratory and confirmatory factor analysis? The difference lies in their purpose, in their assumptions, and how they are used in the research process. So, first, in terms of purpose, exploratory factor analysis tries to discover the underlying factor structure of a dataset without predefined expectations. So, what are the key characteristics that is used in early research stages? That there are no prior assumptions about how many factors exist. The goal is to identify here patterns and grouping among variables. Factors are derived from the data. It is often used to reduce dimensionality of developed theory. And give an example, when a psychologist, for example, wants to develop a new personality test and wants to explore how many traits it actually measures. So these are the key characteristics of exploratory factor analysis. Discover the underlying factor structure of a dataset. I gave you an example. And on the other hand, we have the confirmatory factor analysis. Here we use this type of analysis when we want to test whether a hypothesized factor structure fits the data. What are the key characteristics? This is used in later research stages. The first one is in early research stages. This one is in later research stages. When the number of factors in the item associations are pre-specified, on the other hand, we said that here we try to discover an exploratory factor analysis, the underlying factor without predefined expectations. Here, the number of factors and the associations are pre-specified. The goal is here to confirm or reject the theoretical model, very important. It's a part of structural equation modeling. And some goodness of fit indices assess how well the model fits the data. Let's give an example for this also. After developing a theory that depression consists of three components, for example, cognitive, emotional, and physical, a researcher uses confirmatory factor analysis to confirm the structure using survey responses. So we can see here the comparison table. The first one, exploratory, aims to discover latent structure. The confirmatory factor analysis to confirm hypothesized structure. With the first one, we don't have any prior theory, any model, any theoretical framework. The other one, we try to confirm or reject a precise theoretical model. With in the exploratory framework, factor analysis, the item-factor relationships are known. The other one, they are predefined. The first one is used in early stage, the other one in later stage. And for the software support, the first one we can use, for example, SPSS, R, Python. For the other one, we can use Class, Amos, Lizrel, R11, etc. Now, what about machine learning now? It is very trendy nowadays, and predictive modeling. Anyone who is interested to learn things about machine learning should start by three different types. What is unsupervised learning, supervised learning, and reinforcement learning? Supervised learning has to do with labeled data. Labeled data where both the inputs, features, and the correct output labels are provided. When we can use this in research, when we want, for example, to predict outcomes based on known examples, when we want to evaluate model accuracy using metrics, when we want to use it in medical diagnosis, in economic forecasting. In medical research, we can predict, for example, disease presence from patient data with X-rays, lab tests. In social science, we can predict voter behavior from demographics. Or education research, grading essays use pre-labeled training data. So, and of course, the algorithm, linear regression here, decision trees, support vector machines, neural networks for classification or regression. So the first type is this, I think it was clear. The second one, unsupervised learning, has to do with unlabeled data. And the goal here is to discover hidden patterns or structures in the data. When this is used in order to explore unknown patterns or when we want to group data without prior labels, for hypothesis generation, for data preprocessing or dimensionality reduction. So in genomics, for instance, we can use it in this case. For example, clustering genes with similar expression patterns. In marketing, when we want to segment customers based on their behavior. In cognitive science, we want to discover patterns in brain imaging data. And algorithm, we can mention hierarchical clustering, the principal component analysis. We have explained this in the previous session, and autoencoders. And the third type is reinforcement learning, when someone learns to make decisions by interacting with the environment, receiving rewards or penalties. So we use it in order to learn optimal strategies in dynamic environments in research. We use it when we want to conduct simulations in the behavioral modeling, adaptive systems, in robotics, in game theory, decision-making systems, and in robotics research, for example. Reinforcement learning can be found when we want to teach, for example, a robot to walk or manipulate others. This is reinforcement learning. Or when we want to adapt treatment plans or drug dosing in healthcare, when we want to model market strategies or adaptive agents. And the key concepts are related with reward, always with value function, with policy, and algorithm, Q-learning, deep Q networks, policy gradient methods, and others. So here you can see the summary table, the comparison. Supervised learning is labeled, the other one unlabeled, and the other one is interaction-based, so reward signal. The first one, the goal, supervised learning aims to predict outcomes, supervised, unsupervised learning to discover hidden structure, and reinforcement learning to learn optimal actions. Supervised learning is really the output that we want to take has to do with predictions. The other one, so unsupervised learning, has to do with patterns, with clusters, and the reinforcement learning has to do with action strategy. We mentioned about some examples, disease prediction of supervised learning, in unsupervised learning, gene clustering, with reinforcement learning, autonomous robotics. Robotics is always related with reinforcement learning. And common algorithm, SVM regression, and neural nets, key means with unsupervised learning, and Q learning in reinforcement learning. Now, how can we evaluate the performance of a predictive model? For example, the accuracy, the precision, the recall, etc. Evaluating the accuracy, the performance in general of a predictive model involves using specific metrics, various metrics, and visualizations at the same time, depending on the type of the problem, classification or regression. So for classification models, here are some key evaluation metrics. Accuracy means here, in this context, proportion of total correct predictions. For example, the use case, it is good when, for example, the classes are balanced. What is the limitation? That it's misleading for imbalanced data sets. The precision. Precision of the metrics, it's the proportion of true positive predictions out of all positive predictions. So here, what is the use case? It's important, precision is important when the cost of a false positive is high. For example, spam detection. Okay, we can use this. Recall. Recall is proportion of true positive predictions out of all actual positives. It is important when the cost of a false negative is high. For example, cancer detection. The F1 score, this means the harmonic mean of precision and recall. It is useful when you need the balance between precision and recall. The receiver operating characteristic curve, here the definition is plots true positive rate, which is the recall versus false positive rate. We use it when we want to visualize performance at various thresholds. And the confusion matrix is a table showing correct and incorrect predictions. So how to choose the right metric? According to the problem type, if we have balanced classes, I mentioned about accuracy, which is the recommended metric. If we have unbalanced classes, we need precision, recall, F1 score, etc. If we have varying thresholds needed, then we're going to adopt the receiver operating characteristic curve. And multi-class classification, then we're going to adopt as recommended metric the macro or micro average F1 confusion matrix. Now, when should traditional statistical models be preferred over machine learning models? This is a question that I think we all must think about. When interpretability is critical, I mean, explanation is important. In domains like healthcare or finance or policy making, you often need to explain why a prediction was made. So statistical models like linear regression or logistic regression provide clear coefficients and confidence intervals, making them easy to interpret. When you have small data sets, for example, machine learning models generally require large data sets to generalize well and avoid what we call overfitting. Traditional models, on the other hand, work better with limited data and can often provide more reliable results in such cases. When the underlying data structure is known, if you understand the relationships among variables, for example, linear or normally distributed, then traditional models that are based on assumptions about the data can be more appropriate and more efficient. For example, using a linear regression when you know that the relationship is linear. When statistical inference is the goal. If you are interested in estimating parameters, confidence intervals, or testing hypotheses, for example, p-values, then traditional models are built for this purpose. Machine learning models generally focus on prediction accuracy, not inference. Remember this, prediction accuracy, not inference. When simplicity and speed matter, because traditional models are typically simpler and faster to implement or compute, especially with structured tabular data and basic relationships. When the cost of overfitting is high, machine learning models are more prone to overfitting, especially on small or noisy datasets. And also traditional models often include regularization or strong assumptions that prevent overfitting. In regulatory or legal environments, regulatory environments often require transparent, auditable models. The traditional statistical methods are easier to audit and justify than black box models. So we can understand when, in which cases, traditional statistical models are preferable than machine learning. Overfitting, I mentioned about overfitting in predictive analytics is a common risk. When a model learns the training data too well, including noise or outliers, resulting in poor generalization to new unseen data. So the risk is here that the model performs well on training data but fails on new data, so poor generalization. Misleading accuracy. High accuracy during training gives a false sense of confidence. Increased complexity. Overfitted models are necessarily complex, making them hard to interpret and maintain. Wasted resources. Time and computational power are wasted tuning models that do not generalize. Bad business decisions. Predictions based on overfitted models can lead to costly or ineffective decisions. And how to avoid overfitting? Through cross-validation. So use techniques like k-fold cross-validation to assess model performance across different data subsets. Train or test split. Always evaluate the model on a separate validation test set to check its performance on unseen data. Regularization, apply L1 lassos, we say, or L2 ridge regularization to penalize overly complex models. Simplify the model, avoid very complex models when simpler models perform adequately. For example, linear regression, this performs easier. And pruning, this means reduce the size of decision trees by pruning branches that provide little power. Really stopping in iterative algorithm neural networks. We stop training when performance of the validation set begins to degrade. So early stopping, we use more data because more training data can help the model generalize better and reduce the chance of overfitting. The feature selection, when here we can remove irrelevant or redundant features to reduce noise. And ensemble methods, techniques like bagging, for example, random forest, and boosting can reduce overfitting by combining multiple models. Now, how can clustering techniques like K-means or statistic means or hierarchical means be used in exploratory data analysis? Clustering techniques are powerful tools in exploratory data analysis because they help you discover natural groupings and hidden patterns in your data without needing labels. So how clustering helps in this? Clustering groups similar observations together based on feature similarity. This allows to do what? This allows to identify patterns, to detect outliers or anomalies, to reduce data complexity, to generate hypotheses for further study. Some key clustering techniques include the K-means clustering that you need to know. When you want to specify the number of clusters in the algorithm, groups data into K clusters by minimizing the distance between data points in the cluster centroid. This is used, for example, in order to segment customers by purchasing behavior, where we want to make a group survey and to cluster group survey response into similar attitudes and opinions. And it can be can help a visualization with a PCA to plot clusters in a two-dimensional space. The hierarchical clustering is another type. It works by building a tree of clusters based on similarity. There is no need to pre-specify the number of clusters. There are two types of this, the bottom-up, top-down, agglomerative and divisive. And it's used when we want to analyze relationships between variables or cases, and we want to identify nested structured data. Here we can use dendrograms in order to visualize how data points cluster at different thresholders. So why use this clustering in EDA for pattern? What is the benefit? The pattern code discovery, because it reveals hidden structured data. When no labels needed, so it works even without predefined categories. For dimensionality reduction, because it simplifies complex data sets. With hypothesis generation, because it helps define groups for deeper targeted analysis. And visualization aid, because it enhances understanding of relationships via plots or dendrograms. The typical steps here in using clustering for exploratory, EDA, has to do with, first we need to pre-process data, so normalize, handle missing values, to choose features relevant to your goal. Then we try to apply clustering algorithm, K-means, hierarchical, whatever you want, and visualize results finally when we scatter plots, heat maps, dendrograms, etc. So exploratory data analysis, here, the typical steps in using clustering for this is what I mentioned before, about the processing, choosing features, applying clustering technique, and visualization. Now, experimental and causal inference techniques. Here, we need to think about what are the common methods of causal inference. The randomized controlled trials, the difference in differences, instrumental variables. Definitely, you need to know about these methods. First, randomized controlled trials. When this is happening, the first one, randomized controlled trials, when participants are randomly assigned to treatment or control groups. Randomization ensures that no systematic differences between groups exist, isolating the effect of the treatment. When to use it, when you can ethically and practically control treatment assignment. There is a gold standard. It's a gold standard for causal inference. An example, randomly assigned students to a tutoring program versus no tutoring program, then compare test scores. Okay, this is a randomized controlled trial. What are the limitations? That is expensive, that is time-consuming, that may have ethical or logistical constraints, and sometimes this lack some external validity. real-world generalizability, etc. The second one, difference in differences. This compares changes over time in the treatment group versus a control group. This assumes that both groups would have followed the same trend without the treatment, so parallel trends assumption. When we want to use this in natural experiments or policy changes, when the randomized control trials are not feasible, but you have before and after data for both groups. Let's give an example. For a minimum wage study, we can compare employment rates before and after a wage increase in one state versus a similar neighboring state with no change. What are the assumptions that this requires that the treatment and control groups would have evolved similarly in the absence of treatment? Instrumental variables. When we want to use a third variable, the instrument that affects the treatment, but only affects the outcome through the treatment. For example, when to use it? When there is endogeneity or unobserved confounding. This is a treatment which is not randomly assigned. It may be correlated with omitted variables. For example, we want to study the effect of education on earnings. We use proximity to college as an instrument. It affects likelihood of attending college, but doesn't directly affect the earnings. Instrumental variables. This is another method. So here, an instrument must be relevant, so strongly correlated with the treatment, and exogenous, not directly related to the outcome. So here, if we talk about the summary, the first one, the randomized control trial has to do with randomly assigned treatment. Differences we compare before and after across groups, and instrumental variables when we use a third variable to isolate the causal path. Other causal inference methods are regression discontinuity design, propensity score matching, synthetic control method. For example, propensity score matching is a statistical technique that is used to reduce selection bias in observational studies, particularly when random assignment is not possible. So how this helps? In real world, when I talk about real world, I mean no randomized studies. Individuals who receive a treatment or are exposed to the condition often differ systematically from those who do not. This introduces what we call selection bias, meaning observed differences in outcomes might be due to these pre-existing differences, not the treatment itself. So what is the solution? Propensity score matching. What is propensity score? The probability that the subject receives the treatment given observed covariates, age, income, health status. So this propensity score matching works in three main stages. We estimate propensity scores. We use logistic regression or another model to estimate the likelihood of treatment assignment based on observed covariates. For each treated subject, we need to find one or more untreated subject with similar propensity scores. For example, the nearest neighbor matching. When we compare outcomes, we try to analyze the outcome differences between matched groups, which are now balanced on the covariates used to calculate the propensity score. So how this reduces selection bias? Because by matching treated and untreated units with similar likelihoods of receiving treatment, this creates groups that are comparable in terms of observed characteristics. And this mimics the conditions of a random control trial where treatment is independent of covariates, therefore reducing confounding by isolating the treatment effect by improving causal inference. So imagine, for example, that you are studying the effect of a new drug on recovery time. Patients who take the drug may be healthier or wealthier to begin with. So without propensity score matching, differences in outcomes could reflect differences in health, wealth, not the drug. And with the propensity score matching, you match drug users and no users with similar health and wealth profiles, reducing bias in comparing their recovery times. Of course, there are limitations because this adjusts only for observed variables. Hidden confounders can still bias results. This requires a good model specification for estimating propensity score. Matching may lead to data loss if suitable matches aren't found. And propensity score matching means that we can reduce, of course, selection bias by creating a matched sample of treated and untreated subjects that are comparable on observed covariates, allowing, of course, for more reliable estimation of treatment effects in observational studies. And finally, before concluding for today, mediation and moderation analysis are two different statistical concepts used in analyzing relationships between variables, especially in social sciences, psychology, business research. The first one needs to understand how or why an independent variable affects a dependent variable through a mediator. And the other one needs to understand when or for whom an independent variable influences a dependent variable depending on a moderator. I think I will stop here because it's a bit a chapter.
Yes,
and,
yes. Yeah. Okay, thank you so much, Dr. Rania. Thank you so much. This wonderful presentation. And thank you so much for coming again. I know you're very busy at office. Still, you make it a point to be present with us. Yeah, of course, we have some shifts in our schedule that were supposed to be yesterday, and due to work schedule, then we push it today. So hope our audience would understand that. And thank you so much, dear precious audience. Thank you for your support, and thank you for being with us patiently, and happy learning. Thank you so much. Bye-bye.
Thank you very much.